So, hello everyone. I'm Namwoo Kang from Smart Design Lab in Korea. Previously, I worked with Panos Papalambros in U of M. And it's an honor to introduce my research to JMD's first webinar. And today, I will not go into the details of this paper, but I want to share with you how our group is applying a data-driven design approach to the automotive industry in Korea. Our group has been addressing this research question. Can AI design engineering systems? We believe that AI-based generative design can change design paradigm. This approach can use both physics and data and make aesthetic, marketable, diverse, interdisciplinary, and human-centered designs by using AI. And the objective is to generate numerous novel designs rather than finding single optimal design. This is our proposed AI-based generative design. The process consists of 3 stages: design generation, design evaluation, and design recommendation. First, design generation stage integrates CAD and AI to generate novel designs based on the past design data. Second, design evaluation stage integrates CAE-PAM and AI to evaluate and predict various engineering performance and manufacturability of generated designs. Lastly, design recommendation stage integrates HCI and AI to predict customers' design preference and recommend marketable designs. Our group is developing this process with Hyundai Motor Company in Korea and focusing on wheel design problem. Let me introduce the design generation stage first. In our previous JMD paper published in 2019, we proposed a generative design that combines topology optimization and generative models, and we applied this method to the wheel design. Here is the key idea of the paper. First, we gather the reference design data from the market. And using multi-objective topology optimization, we create a new design that is similar to the reference design and has a low compliance simultaneously. By varying design parameters such as the similarity weight and design conditions, we can get multiple designs using the same reference. Then BGAN is used to generate reference designs, and the generated designs are used again as BGAN's training data. This iterative design process makes it possible to generate a large number of designs using the limited market data. From now on, I would like to show you how we have been expanding this JMD paper. First, we focused on enhancing design diversity, which is influenced by design parameter combination. We developed an end-to-end network to approximate deep generative design process. Then we proposed a reinforcement learning-based generative design with the reward function, maximizing the diversity of the designs. We formulate the design exploration as a sequential problem of finding optimal parameter combinations in the given design space. After filtering similar designs, thousands of new 2D designs were obtained. These are not existing designs in the market, but they are real product-like designs, and they have high stiffness. In order to generate the 3D CAD models, we built a rim cross-section design generator. First, we gathered the cross-section data from real-field CAD models. Through this again, we created new rim cross-section design. Then we clustered them for sampling representative designs. Now we have disk view and rim section data sets. Then 3D CAD model can be generated using this data. We built image processing, data processing, and 3D CAD modeling process by fully automated programming. After filtering, thousands of new 3D designs were obtained at the design generation stage. These designs are generated by using AI without human help. When we apply AI into our automotive industry, the biggest problem is that there is no useful data. So I think how to generate data using domain knowledge is the most important problem in the industrial AI research. Next stage is for design evaluation. Here we will evaluate generated designs in terms of engineering performance and manufacturing cost. First, we evaluate the stiffness of wheel. We integrated deep learning into Hyundai Motor Company's CAD-CA framework. The proposed framework consists of 7 stages: 2D generative design, dimensionality reduction, design of experiment in latent space, CAD automation, CA automation, transfer learning, and visualization and analysis. The proposed deep learning model can predict the stiffness of wheel instantly. So when industrial designers draw 2D sketches on the tablet, they can obtain engineering feedback instantly without engineers' help. After prediction, we can visualize and explain the deep learning results. The wheel shape affecting the natural frequency can be identified by GradCam, which is one of the explainable AI techniques. For example, 10 wheels were selected from the 10 frequency groups, and the GradCam for each wheel is displayed as a heat map. The results show that an important area highlighted in red is the central part of the wheel. This is because the largest displacement occurred in the center of the wheel in the lateral mode shape. In addition to stiffness analysis, we built a stress prediction model. Here we predict the magnitude and location of maximum stress when the barrier impacts on the wheel. For this, we automated the data gathering process and pre-processed the simulation data. Then we built a multimodal deep neural network using 3D CAD voxel data as inputs. These are examples that maximum stress locations are predicted. The red star indicates the predicted location, and the blue circle indicates the ground truth. It is shown that the locations are well predicted. We also developed 3D deep learning model for estimating manufacturing cost, where inputs are 3D CAD, material, and volume. And 3D grad can visualize the machining features influencing the increase in manufacturing cost. The last stage is for design recommendation. Here, we can predict customers' preference and recommend designs for the target market. For more realistic wheel design survey, we added the texture by using deep learning-based image-to-image translation. Then the online survey is conducted. Customers rank the wheel designs which are generated by AI. The challenging part of preference modeling is that the market is heterogeneous, and it's hard to get sufficient data from a single customer. To handle this problem, we propose a similarity-based ensemble method which can refer to other customers' preference. After modeling, we can find the design which has the highest utility. Then we recommend the best design to each customer. We can also conduct customer segmentation in latent space, recommend the design for the target customers group. Now let me conclude my talk. We propose the AI-based generative design. I believe that the proposed method could totally change the conceptual design process. In the current design process, we have to iterate between designers and engineers with a small number of designs. However, using our proposed process, AI will generate aesthetic, engineering feasible, and marketable numerous designs instantly. Then designers, engineers, and customers sit together and discuss and select the best conceptual design and move to the detailed design stage. This is the end of my presentation. Thank you for listening. What questions do you have?